Hello everyone, welcome back to the video lectures, DSP video lectures on sampling. Today in this lecture, we would be taking a look at increasing the sampling of discrete time signals. Let me show you where we are right now in terms of covering the topics in sampling. We are in the right now in the sixth lecture now. Okay, the first one we had a look at periodic sampling. The second lecture we had a look at how the frequency domain relationships would be there when you are discretizing a continuous time signal. Third lecture we had a look at given a band limited signal and its discrete time samples, how could we reconstruct back the continuous time signal. Fourth lecture we had a look at given a continuous time signal, how can we do a discrete time processing of that signal. For example, what would be the relationship between the impulse response of the discrete time system versus the effective continuous time Fourier transform, equivalent Fourier transform for the continuous time signal. And then in the last lecture we had a look at decreasing the sampling rate of discrete time signals, and in this lecture we will take a look at increasing the sampling of a discrete time signal. Okay, so let me now move on to a desktop mode, sharing the desktop mode, and to the OneNote settings. Right, so this is what we are going to take a look at in today's lecture: increasing the sampling rate of discrete time signals. Okay, so what does that mean? Assume you had obtained x of n initially, which is obtained by sampling the continuous time signal with a time period of t. Now you have increased the sampling rate, okay, by a value L, which means this is equivalent to obtaining samples at this one. Your t here is t by L. Okay, so the time period earlier was t. So what is it that we are going to take a look at in this lecture is how is this x of e power j omega is related to x of e power j omega. As was the case, I of e power j omega is related to x of e power j omega. That's what we should get clarity by the end of this lecture. Okay, as was the case earlier, the objective here is can you once you are able to know this relation, there is not really a need for in order to increase the sampling rate, you could do right away from x of n, and there is no need to go from the discrete time to a continuous time and then resample with a different time period. Okay, here also, like the case in the earlier lecture, we would first do it from the frequency spectrums. Okay, what to expect there, and after that we will do a more rigorous mathematical analysis of it. Okay, let's start. Okay, what we will do now is, let's assume for the continuous time signal, the frequency spectrum of that continuous time signal be xc of j omega. Okay, that is a band limited signal with its frequencies being, highest frequencies being minus omega n2 plus omega n. Okay, for the convenience of drawing these spectrums without loss of generality, let's assume you would see that later that these whatever inferences we are drawing would still hold good when we change these assumptions. Okay, let's say omega n times t equal to pi. This is something we assume so that it becomes we would be able to make much better sense when we are drawing it. It becomes easier for us. And in some places also we would assume that the goal is here to increase the sampling rate by 2. Okay, wherever possible we would avoid that and put just the symbol L, but we would do the other way around in some places. Okay, this assume that this is 1. Okay, yeah, we will at least use this L equal to 2 for drawing, moving from capital omega to small omega wherever this is required. Right, so what we will do now is let's take a look at how does x of e power j omega would look like. Okay, well, this is omega. You already had done it enough number of times now. Okay, this magnitude, what would be that magnitude? That would be 1 by capital T, right? Because you are sampling x of e power j omega with a sampling rate of t, and this would be equivalent to, you are changing the axis by scaling. This is essentially is equal to omega times t here, right? And this being omega n here, omega n times t, let's assume that's pi. So you have this value to be pi, this to be minus pi. Okay, and then the next copy would come at 2 pi. It's because it is periodic with a periodicity of 2 pi. So you have a copy here at 2 pi, and that's how it is, right? Let's draw it for minus 2 pi also. Okay, minus 2 pi, you have that. So this is your x of e power j omega, right? Now what we would do is, let my time period now be t1 equals to t by L. That's the time period. Of course, this is equal to t by 2 here. Okay, so first thing we would do is, let's try to draw that directly, making inferences from here. Let's draw that out. Okay, so what's going to happen? This is your omega, right? And this is equivalent to omega times t1. Now your time period is t subscript 1. Okay, and well, omega n times t is pi, so omega n times now this is getting multiplied with t1. That's nothing but omega times t by 2, correct? So had it been pi, now it would come to pi by 2 here. If this is pi, this should come to pi by 2, right? And this also, this would come to minus pi by 2. If I'm just trying to draw it from here. Okay, and what about its magnitude? Yeah, its time period is t by 2, so 2 by t, or if I generalize that to be L, this obviously would be equal to L by t. Okay, when it is L equal to 2, that would be 2 by 2, 2 by t. So that's how it is, and it's periodic with the periodicity of 2 pi, again near 2 pi. Okay, again plus pi by 2 to minus pi by 2. I have a copy of it. It should have, yeah. Similarly here at minus 2 pi, I have a copy here. So that's what is it that I have drawn now. Increased one. Let me, how am I calling it? Xi of n. So let me call it as the magnitude spectrum of Xi of e power j omega. Right. Now what's our goal is not to infer it from the continuous time domain, but rather try to infer it from x of e power j omega. That's what we'll do now. Okay, let's do it in 2 steps here. First, see, which is there here from minus pi to pi should come to minus pi by 2 to plus pi by 2, right? That width should change. So let's first, as a first step, let's focus on scaling it down, okay, to minus pi by 2 to plus pi by 2. If I scale this axis by that, okay, assume that that function which has it is some other intermediate function xe of e power j omega. What would be that function? You could already make a guess here. The time period is changing, so somehow if you could stretch whichever is there, for example the values at 0, 1, 2, if they can go to 0, 2, 4, that means the distance between the samples earlier is 1. Suppose if that becomes 2, then this is what would bring the spectrum to a width of minus pi by 2 to plus pi by 2. Anyway, that we will work out a little later, but before that, assume that this is something that's scaling things along the omega axis, okay, by changing your simple sampling rate. So that, what would I get out of that? Well, if I apply scaling here, that would give me, for example, this would be pi by 2 minus pi by 2. Notice that that will also bring me the second copy which is there. So whole omega axis you divided by 2. Okay, so that copy earlier which is there at 2 pi would come now to pi itself, right? So well, this is okay, the pi copy is somewhere in between here. Okay, I should have drawn the first one bigger so that these would have looked fine, but still that's okay. So this is 3 pi by 2. Okay, and one more copy here. By the way, this is your pi is somewhere here, and this one more copy here, right? So this is it, which is there at minus 2 pi has come now to minus pi, right? And here what happened, this is at whichever is right, which is there at pi, it is ending, that has come to pi by 2, right? And this another peak was there at 2 pi, now that has come to pi here, right? And this is minus pi, this is minus 3 pi by 2, right? So similarly, if you, yeah, okay, then what is this? Right, so this was actually the original one here, right? So I could write in the similar way on the other side. Okay, so minus 2 pi, so that's, well, I mean, wait a minute, so drawing here was, I should have drawn this pi a larger one, but I'm sure you could now guess it out. So this is 3 pi by 2, right? So where will be the next copy would end here? This is pi by 2 to 3 pi by 2, right? So this each copy is of length, this length is pi, right? So 3 pi by 2, 3 pi by 2 plus pi, that means 2 pi by 2, that would end at 5 pi by 2, right? So centered at 2 pi, so this would be centered at 2 pi, right? And well, that would end at 5 pi by 2, that's there. Okay, and yeah, so 3 pi by 2, this is 5 pi by 2, okay, and so on, right? I could write on the other side also. So now from here, you pay attention here. Well, we made it, by the way, this would still keep this magnitude to be 1 by 2, and 3 pi by 2, this is 2, and this is pi, right? What should I do now to get from here to here? Okay, this is what finally I need to get, right? So, well, what happened now? I have an additional, if I get rid of this copy, the rest of the things would be fine, is it not? I just need to get rid of this copy. So what can I do for that purpose? You apply a low pass filter, right? So that filter should have a value from minus pi by 2 to plus pi by 2. So if I generalize to L, that's essentially should have value from minus pi by L to pi by L. And finally I should get L by T. So this should have a gain of L, correct? And of course the same thing should happen at multiples of 2 pi, of course, because this again discrete time signal, of course this is periodic. So here again, so you just pick one copy, okay, from within 0 to 2 pi. So this is 2 pi minus pi by L, and so on. And of course here there would be similarly one more copy will be there here, right? So if you want me to draw here also, that should be something like that, okay? And another one would be something like that, right? So this is a 2 pi minus 2 pi. Let me call this is an increasing, so let me call this filter by name hi, increasing, I for increasing of e power j omega. So all I need to do now is you multiply xe of e power j omega with hi of e power j omega, correct? And what am I getting here? Well, I am keeping a copy from minus pi by 2 to plus pi by 2. Okay, here L being 2, that's fine. So I am getting here the magnitude is L multiplied with 1 by t. So this is L by t, okay? And well, this is pi by 2, okay? Or I could have written this as pi by L here. Okay, I could pi by 2 that also I could write it. This is minus pi by L. And another copy is at 2 pi. Of course, it's a periodic and that should make sense. I'll get another copy here. Similarly, at minus 2 pi, I'd get a copy. And that's all on both sides. And this is what is x, the magnitude of xi of e power j omega obtained as a result of multiplying xi of hi of e power j omega with xe of e power j omega, right? Hope things are clear to you, right? So what I will do here is just as a practice, I will give you, so far we haven't done mathematical analysis of it, which we will do very shortly. Before that, let me give you an exercise where assume that instead of having it till pi, you have it till pi by 2, minus pi by 2 to plus pi by 2, okay? And then also assume that instead of doing by L equal to 2, you do it L equal to 3 and you draw all these things again there, okay? That's the first exercise for you on this for this part, okay? Your exercise 1 is let L equal to 3, okay? That's what you want to increase the sampling by this. And let me give you how the x of e power j omega would look like. Assume that you have it just from pi by 2 to minus pi by 2, okay? And assume that this value is 1, okay? And this is your omega. And of course the same thing repeats at 2 pi, okay? So somewhere here 2 pi, and you have it there. Same thing at minus 2 pi, and of course it continues on both sides. So what I would like you to do is plot and label, okay, with some approximate scaling the magnitude of xe of e power j omega and hi of e power j omega, and also magnitude of xi of e power j omega, okay? And this you do it for at least minus 2 pi, okay? Or at least over the period of omega varying from minus 2 pi to 2 pi, so that you get a clarity over there, okay? That's the first exercise for you, and that's all we got it. To summarize things, you do this operation as called as a first, so you to get from x of n to xi of n frequency spectrum of xi of n, you could do it in 2 steps. We have done it in 2 steps. One, you do a scaling in omega axis, okay, which there in the time domain is equivalent to increasing the spacing by a factor L there, right? And after that you did a low pass filtering, okay? If you want me to draw it as a block diagram, it's equivalent to this way. If you want me to draw it as a block diagram here, what is it that we have done is assume that this symbolism means you are increasing the sampling, you are increasing the distance by L. Okay, initially you have x of n, you increased that spacing by L, giving you xe of n. To that you do a low pass filtering and giving you a gain of, here gain should be L, and your cutoff frequency should be equal to pi by L, and as a result whatever you are getting is equivalent to, you are then getting xi of n. Okay, so well, xi of n, let's do a mathematical analysis of it. Before that, let me again rewrite the expressions that I have written in the beginning. Let your x of n is equivalent to xc of nt. You sampled it, that means you have taken samples of the continuous time signal with a periodicity of t, and the second one is obtained as if you are taking samples of it with a periodicity of t by L. So here the period of your periodicity with which you have taken samples is t by L. Okay, that's with which you have taken. Now the way we would like to write expander, the first step here, okay, to obtain xc of n from x of n. Okay, let me start with an example so that this becomes very intuitive to you. For example, I have a x of n something like this. Okay, 3 4 0 1 2 3. Okay, this is assume your x of n. Okay, from here getting xc of n would look like, what you would like to get here is, to get a scaling there you need to scale the distances here, which means let's say I still keep it 0 1, but here I make it to 0, and then comes the 2, okay, and then another 0, then comes 3, another 0, then comes 4. Okay, this is 1 2 3 4 5 6. Okay, this is what I would like to get. Now what I would recommend you is to pause the video here and then express xc of n mathematically in terms of x of n. Okay, you pause the video and try it out here. Okay, because the rest of the whole thing is dependent on that. Hope you do that. So this is what you cross check your answer. So this is what you should be arriving at. Your xe of n would be equivalent to k varying from minus infinity to plus infinity, x of k multiplied with delta of n minus k. Make a note here, this delta is a discrete time impulse, not the continuous time impulse. Does that make sense to you? Take a look at here, sorry, n minus kl. So the question is this, if I tell you that I am sampling t by L it is, so you take a look at here. I want this n, for example, you take this xe of n value, you want to compute it at 2, okay, then your n equal to 2 here, for which value of this L is already anyway, assume that this is 2, you are upsampling by factor 2, for which value of k this is non-zero. That means this is, if k equal to 1 means this delta function is non-zero, is not equal to 1. So k equal to 1 means this is going to be equal to x of 1. So this is going to be 1. That means xe of 2 is equal to x of 1, right? For all other values this is 0. Now suppose if you are looking at n equal to 1, there is no way that this delta of n minus kl, so this kl can take values of 0, 2, 4, 6, 8 and so on. So it can never take a value of n. So at 1 this is going to be equal to 0. So this is a very, very important expression required for the rest of the analysis. I'll rewrite it here again. Xe of n is equal to, you integrate it or k varying from minus infinity to plus infinity, x of k into delta of n minus kl. Okay, so the rest of the explanation or analysis is based on this. Well, before that, let me give you one more exercise here to work out for. Okay, that's to find out what would be the discrete-time Fourier transform of Xe of n. Okay, of course you already know it. That's what we have drawn here, right? This is what it is. Okay, that's what we have already drawn, but you would be doing the same thing you mathematically derive, which would give you the same expression there. Okay, to cross check, I'll also give you the answer and give it as if it's something you need to prove. So prove that the discrete time Fourier transform of Xe of n is equivalent to x of e power j omega times L. Okay, this is the second exercise for you. Okay, with that, let me come back to our actual business here. You know Xe of n, you want to get Xi of n. Okay, let's also call this function, we were calling it as the response as Hi of n, or let me call this as Hi of e power j omega. I am following the consistent notation with respect to what I did here. Okay, now let me express in the time domain the relationship between Xi of n and Xe of n first. Okay, so this is Xe of n. This, now the impulse response here is Hi of n. What does that mean? If I give delta of n, what I get as an output is Hi of n. So I have a summation of scaled and shifted deltas. So what would be the output here? Well, that would be scaled and shifted versions of the impulse response itself, because for this is an LTA system. For delta you have got Hi, so for delta of n minus kl, Hi also would be shifted by kl value, and of course the multiplication by constant would remain same. So what could I write here? Let me write here the Xi of n, that is the output of applying the low pass filter, would be equivalent to summation over k varying from minus infinity to plus infinity x of k into, since I considered the impulse response is Hi of n, okay, that this output of that would be Hi of n minus kl, another important result. Now it's time to compute what exactly is Hi of n. We know its frequency response, that being a low pass filter. So within, you express now Hi of n, you need to compute it Hi of n from its frequency response, right? What is the usual? This is, notice that we are in the discrete time domain. So well, Hi of e power j omega is continuous and periodic with the periodicity of 2 pi. So you integrate it over a period of 2 pi, that being a continuous variable, and that's where you take Hi of e power j omega, and it's a complex exponential e power j omega n, and output is in terms of n, so my integration is with respect to omega. So this is the expression. So that means, now let me simplify this further. Okay, it has value only from we have seen this, right? This low pass filter has value only from minus pi by L to plus pi by L. So let me put here the limits. Let me change it to minus pi by L to plus pi by L, and over that its value is capital L. So let me bring that out also. Okay, and then I have here e power j omega n integration with respect to omega. So what do I get here? This is equivalent to, if you remember, this is something we solved earlier, L by 2 pi into e power j omega n, derivative is with respect to omega. So what do I get in the denominator? Jn, to which I need to apply, substitute for omega the values or the limits minus pi by L to pi by L. Well, that would give you sine, 2j sine is what you get there, correct? So this would be equivalent to 1 by, what do I have so far, 2j times pi n. Of course this is not 1, I have already L here, okay? And what do I get here? 2j times sine of, in place of omega I am substituting, so pi by L, and of course n would remain there, cancel out this. So that means, what's the expression for hi of n? That's equivalent to sine of pi by L times n divided by, I take L to the denominator, so in the denominator I get it as pi by L times n. Very familiar expression by this time to, I guess, all of you. So that's what is hi of n, right? Given hi of n, I know what is xi of n is this, right? So you substitute there, so that's shifted by kl and then sum up over my k varying from minus infinity to plus infinity. So what do I get there? What's my final output? Xi of n, that's equivalent to k varying from minus infinity to plus infinity. What do I have here? X of k, that would remain same, and in place of n I should take n minus kl. What will that give me? Sine of pi by capital N into n minus kl, okay? Same is the case in the denominator, pi by L into n minus kl, right? That's all. That's the final expression in the time domain for the signal obtained as a result of upsampling the signal, and this signal being expressed in terms of the discrete time signal x of n itself. Okay, do you see something, this similarity of this to something we have already dealt with earlier? I guess you already see that. This is the interpolator that we got while you are reconstructing from x of n the continuous time signal. The only difference from there to here is your output signal there is also a continuous time signal xr of t. If you recollect that it is represented by x subscript r of t, right? Continuous time signal. And instead of x of n, there we converted it into xs of t, and then we gave the expression there from, so that reconstruction is essentially is an interpolation you are doing in between. This is also an interpolation that you are doing. There you had a continuous time sinc function. You have something very similar to that here. This is again a discrete, somewhat discrete equivalent to that. And again, you are not new to this function. This you have dealt with it earlier. Okay. Are there any problems with this? Is the ideal reconstruction filter when you are increasing the sampling rate of a discrete time signal, as it was the case earlier. This involves the sinc functions for into an infinite length, and assume that k is very large, that something interpolates you in the middle. Okay, by the way, also pay attention here that this original x of n, which are the values are there, now those values will be placed at 0, L, 2L, 3L, 4L, and so on, integer multiples of L. And you notice here those the sinc function properties which we discussed in the last class or class before that. It would, other sinks will not contribute anything here, because its values other than when the inside function becomes 0, other all other integer multiples of L you would have that 0, so that keeps the values intact. Okay, while you are expanding, that ensures that its value is intact at, for example, it's 0, 2, but only in between. That's what it interpolates. Okay, that interpolation contributed by multiple sinks. And then well, in practice you might not, for most of the applications you might not go with this sinc function. So you see here, let's come back to this this block diagram. You would still use this upsampler, but this is something, instead of this low pass filter, ideal low pass filter is not practically realizable. So something we would take a look at least before we wrap up this topic on increasing the sampling rate, okay, of a discrete time signal. Let's look at one practical. Let's write it as simple practical interpolation filter. Simple practical interpolation filter. Let's see one simple linear filter that is good enough for most of the purposes. Okay, let me first write the mathematical representation of it, and then I'll make it clear to you. Say for example, this let me call with h subscript lin, lin for linear, okay, of n could be written as, looks somewhat complicated in the beginning, but once we make the analysis, it's a very simple filter. Absolute value of n by L, for example 0 less than or equal to n less than or equal to L, and 0 otherwise. Okay, let's try to draw this so that it becomes you will realize that this is extremely easy to understand. So let's assume a value of L equal to 5 here, and let's draw how it looks like. Okay, this filter looks like, let's draw it on both sides of n. So 0, 1, so anyway it has value from 0 to L, that means here L equal to 5, so 0, 1, 2, 3, 4, 5, let me take here. Similarly here -1, -2, -3, -4, -5. What is its value? At 0, 1 minus 0, right? So that's equal to 1, right? So this value is, assume this is 1. And what about it 1? 1 minus 1 by 5, 4 by 5. So that would be 4 by 5. Yeah, it is symmetric because you are taking absolute value. So this also has to be 4 by 5. For n equal to 2, 1 minus 2 by 5, 3 by 5. Well, same thing here, 3 by 5. Then 1 minus 3 by 5, 2 by 5. Same here, 2 by 5. Okay. What about here? 1 by 5. 1 by 5. Right, at 5, 0, 0. And of course, for any other values greater than L, this is anyway zeros. Okay. This is the filter, linear filter, with which you convolve a given signal. Okay, I screwed it up. That's a straight, yeah, this is a straight line. Okay. Well, so this is what the signal that this is the kernel with which you convolve. By the way, this is symmetric, so flipping would still give you, this is n, this is your H linear filter of n for L equal to 5. So to give you much more intuition to this, let me show you with bit more explanation here. Okay, I hope you could see. Yeah, let me come to a presentation mode here and go back here. Okay, yeah, so this look at here how this does. So this is something on the expanded signal we would be applying, right? So take a look here. So for example, I want to find out its value at this point. Okay, this, oops, so at 0 I want to, I wish I can write, let me check that out. This, I use a pen here. Yeah, I'm right, able to write now. Okay, so assume that this is where I want to find out. So if you want to find out its value, what you would do here, this is 1, 4 by 5, 3 by 5, 2 by 5, 1 by 5, 0. Okay, similarly I have this on this side. Okay, 4, 3, 2, 1, 0. There is anyway not there. So the value whichever is there is retained. The same thing, even you look at, so basically xe of n, how do you get it? From x of n, in between you keep 4 zeros there, right? You move them, like for example, this is 0, 1, 2, 3, 4, 5. Okay, next one would go to 10. So 6, 7, 8, 9, 10, 15 and so on. So you notice here, whichever is there at multiples of L, that would be retained. And now assume that I need to compute its value at 1. So what's happening there? If I, let me use, oops, what happened here? Yeah, let me use an eraser here before I go further. So let me erase this out. Assume that I want to find out its value at 1. Okay, so what is happening here? Just pay attention here. So this kernel, you are going to convolve it with a kernel which has a value 1 here, right? Here 4 by 5, right? And then this is 3 by 5, sorry, this is 1, this is again 4 by 5, 3 by 5, 2 by 5 and 1 by 5. So what it does, it gives 1 by 1/5 of the value at L equal to 5. Okay, so this value is equivalent to 4/5 of x of 0 plus 1/5 of x of 1, right? So suppose I want to compute it to 2. What's now happening? You shift the whole thing. This is 1, this is the center, this is 0. You shift the 0 to 2, then what it is does, this value would be equal to 3/5 of x of 0, okay, plus 2/5 of x of 1. Well, you go far away from x of 0, the weight would be reducing. You come closer to x of 5, okay, then the intermediate values, the value is increasing. So that's essentially a linear interpolation that you are doing. Okay, hope this is clear. So as you could already notice, those values which are at integer multiples of L, those values are not disturbed because of the way the linear interpolator or this impulse response has been created. It has only value effect for the intermediate values, and it gives more weight to that multiple, that value which is there at multiple of L, which is closer to it. So for example here, for this point, okay, 4 by 5 weight is given, 1 by 5 is given, 3 by 5, 2 by 5. This, what about this? 2 by, it's exactly, you could see here, then the next value, for example here, okay, you give 2 by 5 of x of 0 because that's essentially the distance from that point, okay, plus, so more the distance, less the weight is, okay, because it's far, so it will have lesser correlation with that, plus for example 3 by 5 times of x of 1, and this goes on. Okay, hope this usually this kind of linear filters are good enough in practice. Okay, so you would go with them for all practical purposes, right? Yeah, this is something you could use if you are implementing something. Okay, with that we are done. Let me also give you an exercise, one more exercise here for this, particularly for this filter, exercise 3 of this video lecture. What I would like to give you is, I have given you the formulation here for linear filter in the time domain. Now again, I will give you the answer also so that you could cross check. What would be the DTFT of this? Any guesswork? Any guesswork on how it looks like? Well, this is something like a triangle. In the time domain, how do you get a triangle? A rect convolved with rect would give you a triangle. So time domain, this is equivalent to convolution between two rects, which is their equivalent to something like a sinc function here, right? Similar to this, you would be getting there this function, right? Of course, not exactly this, something similar to that. So that multiplication. So that essentially I'll give you the answer also here. This would be equivalent to, in fact, 1 by L into sine of omega L by 2 by sine of omega by 2 whole square. Okay, this is the exercise given to you. You do it out. Again, by the way, this is also there in the exercise problems of Oppenheim and Scheffer. So once you try it, if you don't get it, or if you have anywhere struck, or if you want to see how this has been done there, you look at the key of it. Okay. Yeah, that's pretty much, we are done now with the increasing the sampling rate of discrete time signals. Okay. Yeah, by the way, just before that, let me come back here, put it in the read mode, and yeah, so again you could see here in this graph, that's essentially that rectangular block is something you had which is the ideal low pass filter. Okay, this is the one which we have seen now. Linear interpolator would give you the other one, which is of course it would not completely avoid the frequencies. There will be a little weight given to that. Okay. Yeah, with this we are pretty much done with increasing the sampling rate. Okay, and in the next video lecture we would look at changing the sampling rate by a rational number. Okay, that's what we would see in the next video lecture. Okay, yeah, I'll stop here. Thanks for watching. If you have any questions, post them in the comment section or discuss them during our Zoom session. Right, thanks, bye.